So far, what we've talked about is transport in the subsurface to the kind of equilibrium condition where it's held by interfacial tension. I think that's the assignment you have going on right now, talking about or perhaps last week you had the immobile contents and you could only dissolve it. The last three sessions, 3.1, 3.2, 3.3, we've been talking about how dissolved components get transported downstream, and how their concentrations vary with location and how they evolve with time. And what we haven't said, but was implicit in it, is that we've been dealing with things like chloride ion, which are conservative. And so what conservative means is that any amount of chloride ion that gets dissolved in the water stays in the water as it goes down gradient. And for some classes of contaminants, organic contaminants for instance, they dissolve, but they also are removed from solution by sorbing onto the media they pass through. And since the mass balance that we apply for the flow equations are related to the porous part of the aquifer only, then any amount of mass that is taken out of the system and plastered onto the grains is something that is lost to the overall flow system. And so I suppose that you'd expect that if you're potentially removing components from the flow system and anchoring it to the static porous medium, then you'd expect that if you assay water downstream in those systems that are non-conservative, that the concentrations in water would be both lower, because you've lost some to the solid medium, and also be progressing more slowly down gradient, because you've been taking it out of the porous medium and not allowing it to go downstream. So the two words, retardation and attenuation, refer to each of those things. Attenuation means it's removed from the fluid system and attached to the grains, the static grains, and therefore the concentration has to be lowered in the fluid phase. And retardation means that it potentially goes slower as it migrates downstream, not like the chromatographic differentiation that you see when you take in your high school a piece of filter paper soaked in water and put it into a dye. You see the colors coming out at different velocities as they wick up the filter paper. And so that's what we'll talk about today. That's our interest today. And so retardation means it travels slower, attenuation means that the concentrations are less. And so we'll talk about this. So you've seen some of these things in your previous lives, in previous classes, I think. I guess I could do this. It relies on the fact that we have sorption occurring, and so you must know plenty about isotherms in your major already. We can talk about how we might measure what those isotherms are, and exactly we can look at what the behavior looks like both in porous media but also in fractured rock. And so that's the things that we'll talk about today. So I won't use these notes at all because they're too long-winded, and I can do it much more compactly. And so I can do it on one page. One page that was written in class, but I'm not planning on writing it today, and it's this page here that kind of summarizes everything that we were doing. November the 25th, 2021. So that's when I did this. So some of this is background, right? The point is that we talked about much of this material in topic 2. Topic 2 was you have a spill, you develop a chimney, it drops to where it's held by capillary forces. Those capillary forces may be due to lenses, may be due to a full capillary barrier. If it's an L-NAPL, it might be due to the buoying of the water table. But regardless, you end up with some distribution of component within the pore space. It doesn't completely fill the pore space. Some of it is water filled, some of it's NAPL filled, and therefore it allows water to flow through it according to what we know about relative permeabilities. And that means that as it goes through it, it dissolves. If it dissolves, then it's present on the downstream side in some concentration. And the stippling that you can not see on your copy of this refers to the fact that there's some component that goes downstream. We spent a lot of time on the recapping the transport of the conservative species last time at 3.3, when we talked about the whole of the system, kind of given in schematic by this input, output, and within the sample plot. And what we decided was that if you have a pulse that is suddenly turned on at some concentration, it will move down gradient. It will move down gradient a length which is equal to the advective velocity multiplied by time. And it will give a sharp front if the Peclet number is very big. And if the Peclet number is smaller, it will give a diffuse front. The Peclet number is defined as velocity times length over dispersion, longitudinal dispersion, I hope, VL over D, yeah. And so as this dispersion coefficient gets larger, then it changes from being plug flow to being this graded curve at the front. And we explained this in terms of fingering occurring at the front. The consequence of this is that at the recovery location, again shown in green and blue, is that a sharp front will come out as a sharp front. The dispersed front will come out as a dispersed front, with some arrivals before you'd expect the original front to have arrived, because some of these fingers are very fast moving, faster than the average, and so they arrive. And some of the fingers, between the fingers, are traveling slower. So you end up with a distribution of concentrations in the arrival. And so that's what we've dealt with so far. And I guess we know that since velocity is equal to length over time, then the time taken to come would be equal to length over velocity. Right? Length divided by length times time divided by time is time. And so that is kind of our simplistic view of things. We know that that's not true. We know that's only true if the Peclet number is greater than 10. If it's less than 10, then this arrival time of the front with 50% concentration and this particular time doesn't hold, and we have to use those other plots, which we talked about last time. So everything we've talked about so far is for conservative species. So now what we'd like to do is we'd like to account for the fact that it's picking up solute here to some concentration. It's going down gradient through this porous medium, but as it travels through here, it's able to be recovered from the water and attached to the porous medium. And so we could think about sorption onto the grains. And so I'm going to go through all of this, but I'm going to skip down to this first to explain exactly what I mean. And so an understanding of sorption would be if you took a beaker, and in that beaker you filled it up with your aquifer, and you put into your aquifer the fluid that's coming through here at some concentration of the aqueous phase. So maybe it's 1 milligram per liter, 1 part per million. And so it comes in here, and you put it in contact with this aquifer, say it's quartz, and you leave it in there so that the solute that's dissolved in the solvent, the water, sorbs onto the outside of these grains. And so the equilibrium concentration on these grains is given by C star. So if you look at this process occurring over time, then what will happen is that you dump in the solute, and initially the concentration that you'd measure on the grains if you pulled them out would be nothing because it hasn't had time to do anything. If you leave it for a little while, it will build, and ultimately it will reach some equilibrium. And so this is when all the sites for sorption are completely filled on the surface of the quartz, and it won't change anymore. So this is if you introduce fluid at some concentration C1, it will go to some equivalent C star. If you double that concentration, you'll go through the same process. You'll reach some kind of equilibrium. And actually this concentration, if it's a Langmuir linear isotherm, then it will be double that magnitude. So a linear isotherm says that if you take this elevation here, for each of these, and you plot them here, and you plot them relative to the liquid concentrations that you're putting in, C1 and 2C1, then you would end up with 2 points, and you can draw a line through those 2 points. And that line, if it's linear, then it's a linear isotherm. If it's curved downwards, it's nonlinear. And so it can either be a Langmuir or a Freundlich isotherm, it doesn't matter. We'll use linear isotherms in this class. And so the idea is that this is both a linear system. You double the concentration of the liquid, you double the concentration that's sorbed onto the grains. It's also reversible. So if you now reduce the concentration from 2C1 to C1, then you'll reduce the concentration that's applied on the grains. And so that's kind of implicit in this. So that's the basic experiment that you would do. And so if we have a graph that looks like this, then just as in the habit of things that I'm interested to draw, this would be change in the concentration on the solid, and this would be change in the concentration on the liquid, right? It's just these axes. And so the gradient of Kd is just equal to 1 times Kd by definition. And so what we could do is that in our aquifer, we're going to assume that this time here is very short, so that we're always at this equilibrium. As soon as you put it in, it immediately goes to here. It's probably quite a good assumption, because these happen quite quickly on the scale of chemical sorption versus millimeters, centimeters per day in terms of transport. And so it's probably not a bad assumption. And so what we can do is we can take our advection diffusion equation, or dispersion equation, which we had before. Accumulation is equal to the mass in minus mass out that occurs due to Fickian diffusion, and the mass in minus mass out that occurs by advection. In other words, a beaker with ink in it being carried across the room, you're advecting that ink by the movement of the water that's carrying it in a beaker. And so that's exactly what advection is. But we could add another term. This is an accumulation term. So it says how quickly the mass of the solute is accumulating in that differential volume. And so we could have a term that represented an accumulation by a different mechanism. And the accumulation by a different mechanism would be a negative accumulation, because you're taking it out of the water and you're putting it onto solid grains, and then it's lost to the system. And so that recovery from the water is defined as the density of the aquifer, here, bulk density of the aquifer. So probably something like 2,500 or 2,000 kilograms per meter cubed. Wouldn't be an unreasonable number. 1,000 for water, right? Theta is the volumetric moisture content. So it has no units, so it's the proportion of the aquifer that's filled with moisture. And so porosity, you'll remember, is the volume of the voids. The volume of the volumetric moisture content is equal to the porosity when it's fully saturated, and it's equal to 0 when there's no water in it. And so the upper bound on this has to be the porosity. So this would range between 0 to 30%. Something like that. And then we can multiply it through by, for now, ignore the term to the right of this, by dCdt. So the amount of mass that we're losing is going to be proportional to the amount of mass that gets desorbed onto the solid, because it has to come from the liquid, and therefore it's net removed from the liquid, and it's a rate that occurs with time. And so this term here has to be the same units as this. And so clearly the concentration change with C star can't be the same as the concentration of the liquid, right? Because this is not non-dimensionless. This is in units of kilograms per meter cubed divided by a number. So the units of this have to be in the ratio of milligrams per liter divided by kilograms per meter cubed. Has to be, right? Just for apples and apples to mix up. So the concentration of the solid, I guess I didn't define it here, but let's see exactly what that should be. I guess we could work it out. It has to be, so this C star equals C. And so C has to be so these terms go out. So C star has to be milligrams per liter, meters cubed kilogram. Strange units, but let's live with it. So we need to define that. So now, at least this should be homogeneous in terms of the units, because they're all saying the rate at which you accumulate fluid by mass arriving in the system, and the rate at which you deplete mass of solute by sorption. We could multiply this now by 1. So multiplying it by dc over dc is just multiplying by 1. And if I then isolate this component, we have concentration, aqueous concentration changing with time, so exactly the same units as this. But now we have another term which is in here, which is dc star over dc. That's exactly this, right? So by doing this experiment, putting the fluid in here, measuring the concentration on here, we get the slope of this curve. This curve gives us this value of what's called the distribution coefficient. K sub d is the distribution coefficient. I guess because it describes the distribution of solute between the water and the solid. And it's defined in terms of this term, and so we could substitute dc star, if I write it here, it's going to be distribution coefficient over 1 is equal to dc star over dc. Exactly what this term is. So we're going to change this number here to being Kd. And so now we have density, Kd, volumetric moisture content, multiplied by rate of change of concentration with time. And so since we have on the right hand side dc dt, we could take this term, subtract it from both sides, or add it to both sides, I guess. Add a term here for this, and you'll add a term here, and you'll end up with this equation down here. That's all we're doing. And so what we've done is we've come up with a coefficient that says something about how much will be sorbed onto the porous medium. I guess if Kd is very flat, then it means that a big concentration in the water will give you a small concentration on the solid. So if it's a very small number, there's no sorption occurring, and so this will go to 0. And if Kd is very steep, it means that a small concentration will give you a big concentration on the solid. And so it makes sense that the effect of that concentration is included in the one term here plus this term, which is this. Forget this. Control Z. So this is the same equation we had here. All we've done is that I have subtracted this term here off the left hand side, and it exists here. And we notice it's the same equation. It just has some different coefficients. Instead of this coefficient being 1, it's 1 plus. This coefficient being dl, it's the same. This coefficient being the advective velocity, it's still the advective velocity. I'm not sure what the t is for. I'm going to take that out. So this is referred to as the retardation coefficient because it retards the transit of the plume downstream, is the reason for it. Since Kd is always positive, density is always positive, and usually moisture content is usually greater than 0, then this term is always greater than 1. So R would be greater than 1 and less than infinity. We don't know what the bounds on this are. And that other than that, this is exactly the same equation that we've dealt with before. So what we could do then is to do what I erased. If we're calling this the retardation coefficient, we could divide both sides through by 1 over r, or multiplied by 1 over r, which is what this is. And if we do that, then r times 1 over r means that this term becomes 1, and we get this final equation down here. So the punchline of everything that I'm saying to you is that if we can define a parameter Kd which defines the sorption, then we can rewrite our advection dispersion equation quite logically, I think, to include that effective sorption, and it comes out to look very similar to what it was before. It's 1 times dc dt, that's exactly what it was before. It's the dispersion coefficient divided by a number which is bigger than 1, potentially much bigger than 1. And an advective velocity is reduced by, again, the fact that this is a number equal to 1 or larger. If sorption is 0, then this term would be 1, and the equation would be divided by 1 just as we had before. If it's not equal to 0, then it's going to be bigger than that. And so the implications of that are that if we think of, and I'll draw it separately, it draws a straight line if I stop at the right time. So this is, so I'm going to go back and draw this. I'll come back to that later. And if this is the output in terms of time. So these are the two. I'm not going to do the upstream boundary condition. So this is C over C0. So what do we have? For the conservative species, I'll just use the same colors, black and green. So length is equal to velocity times time, advective velocity. This will look like this. And this length, time, what do we have? Velocity is equal to length over time. So time is equal to length over velocity. These are the advective velocities, of course, right? So this is the case where dl is equal to 0. If we have dl not equal to 0, then it will look like this. Right? And so that defines exactly the behavior of this. So now what happens if we think about what the meanings of these two components are? So a magnitude of dispersivity makes this less sharp, and so increasing the value of d makes this canter over. This represents how quickly it moves downstream. So if we're reducing this by some amount, we'd expect that if we look for the effects of sorption, then our new curve would look like this. And I suppose the length would be given by our renewed coefficient, which is the velocity divided by r. So this would be the length traveled is equal to the velocity divided by r times time. Always greater than 1, and so it lags behind. And so this retardation is just a function of the value of the retardation coefficient, not surprisingly. I suppose if we wanted to think about what would happen then if we now allow it to be, this red one would be for plug flow. If we allowed it to be dispersed at the same magnitude of dl that we have here, then we're dividing that dispersion through by a coefficient which is bigger than 1. So it would reduce this effective dispersivity. So it means that it would kind of self-sharpen the plume, sometimes called self-sharpening. So the dispersion at the front would be much less. And you could rationalize that because we're reducing the amount of dispersivity, and if you reduce the amount of dispersivity, you bring it back to the vertical. Likewise, we could think about what this would mean at this end. Again, we could write, for the case of the retarded behavior, that the time is going to be equal to the length divided by the advective velocity. But it's not the advective velocity, it's the velocity divided by retardation. So it would be B over R. So I'm going to write it better. T times, so it goes on the numerator. So it would be L times R over V advective. This number is always greater than 1, equal or greater than 1. So what would it look like? It would look like this. And if we had, this is for dl equals 0. And if that's not the case, then I guess this would be something like this. This would be quite sharp, quite vertical. Again, because it's reflecting this behavior here, that when it arrives, it's sharpened. Its arrival is sharpened. And so that's it. That's all. That's all we have to know. So we now have to be able to figure a way to be able to perhaps get a value of kd. We know kind of how to do that. It's just a rudimentary magnitude. And if we know what that value of kd is, we know how to combine it with some other parameters to get a retardation coefficient. And we know that that retardation coefficient allows us to rewrite the advection dispersion equation in this way. And therefore we can use every equation we've defined before, but just modified in terms of the parameters. And so to kind of make that point, you remember that last time we talked about in our notes, perhaps I should, if we go back to, I think it was at the end of 3.1, we have this figure out of Fetter, this equation here. And so if we have this expression here, and I go back to red again, remember that we said that only if it's infinite Peclet number do we get this breakthrough front. If it's a Peclet number which is less than that, it still kind of goes through the 50% mark and kind of goes at one pore volume, but it's cantered over. But as we get larger Peclet numbers, this is a Peclet number of 1. Then no longer does it go through the 50% mark and the 0 pore volumes mark. And so we have to be aware of being able to use that. And so it would be nice if we could use this figure to be able to represent this behavior again for our system. And I guess the punchline is that we just need to use a dispersion coefficient, which is modified to be dispersion coefficient over retardation. and a velocity, which is a velocity divided through by retardation. Those are our modified parameters that we're using. And so we use these parameters, which are shown here, T sub r, which is equal to, I should get it right this time, velocity times time over length. Length is of the aquifer. And we used a Peclet number, which was equal to a velocity times length divided by d, right? Yes. And we knew that for a value here of 1.0, this is C over C0. This is 50% here. Then I guess this is what our curve looks like for Peclet number equal to infinity. This is what it looks like for 100. And this is what it looks like for 1. So we'd like to be able to use this curve, but we have these modified values we have to use. So what we need to do is just modify Peclet number by including these two values. So Peclet number is velocity divided by dispersion. Velocity is divided by r. Dispersion is divided by r. So that's kind of convenient. We don't care. So the Peclet numbers won't change because this is going to be equal to 1. So when we do the calculation here for our new system, whatever the water is flowing at physically, that's the Peclet number we need to use for this advective velocity. But if we look at the magnitude of the pore volume number, remember this number is equal to 1. Advective velocity times time is the distance the front has gone as you've put in that amount of fluid. And it's at the end of the core. So when it's equal to 1, it means you've replaced 1 pore volume. So you've pumped enough fluid in that you've replaced 1 pore volume with your new fluid. And so here we only have one velocity that we have to divide through by r. And so we have this. So the magnitude of the pore volume is just a number that we'd have to divide through by r. And if we do that, then we can use all the expressions that we've used before to be able to solve our system. So that's kind of the punchline. And so that's what we're attempting to do. Okay. So the bottom line is that, and I think there's one figure in this which kind of epitomizes this. Not drawn this time, but drawn previously. It makes that case. This figure at the bottom. So these are the two important behaviors. Is that the retardation retards the front, makes it go slower because it's sorbing material. And so it's retarded by an amount that's equal to the ratio of the velocities. The conservative velocity divided by the non-conservative velocity. And it also sharpens the front. So it effectively reduces the dispersion because you're dividing through this dispersion by some number bigger than 1, and therefore it reduces the magnitude of the true dispersion into an effective dispersion. And so you'd expect the curves to look like this. We should be careful in doing this because we know that this is only kind of a helpful idea for us because it doesn't, it's only really true for big Peclet numbers. Not quite true for others. So we have to be mindful of that. So how can we use that in a useful way? Well, we've made the point that we can define a parameter. And if we can define exactly what this is from our experiment, and we showed you exactly what the experiment is, then we can get that. We know the parameters for our aquifer quite well, but this wouldn't be a very easily determined number. We could get it from field observations if we wanted to, by thinking about what the meaning of this is. And so if we think about the fact that here, the ratio of Vx divided by Vx over r, right? So this is the retarded velocity. This is the actual velocity. This is going to actually equal r. So the definition of the retardation is the velocity of x relative to the retarded velocity. So in other words, the ratio, if you measure a non-conservative velocity which is equal to 10 meters, and your retardation coefficient is 2, then the real front has gone 20 meters. It's just the ratio of those two velocities. And so what we could do is we could use this definition to be able to define the magnitudes of how far the front's gone. And so the other way we could do it is the retardation would be the length traveled by the conservative front divided by the length traveled by the non-conservative front. It's gone 20 meters. The non-conservative plume's gone 10 meters, so the retardation is a factor of 2. Quite a rational behavior. So what we could do is we could do that to try and figure out what the magnitudes of dispersion were in the field in reality. And you remember last time we talked about 3 experiments. One was in a core. We said that's no good because the core is not a very representative sample of the aquifer and doesn't include all the heterogeneity, which is the essence of the dispersion, which occurs at much larger scales. So core is no good for us. We talked about single well pump in and pump back out tests and twin well pump in back out tests. And we decided that those are better because they're a larger volume. So it would sample some heterogeneity, but because the flow regimes that we set up have their own geometric dispersion in them, that the results we get are completely swamped by that geometric dispersion, and therefore the dispersion we measure isn't really representative of the behavior of the aquifer. And so those are no good. And so what we'd like to do is use an experiment that tests it at a big scale, and also at the kind of flow rates that we expect to have in the field in our real system. And so we zoned in on the idea that we could do a natural gradient flow test, where you put something in, chloride in our particular case, and let it go downstream. We could also do that same experiment with other components. We could do it with carbon tetrachloride and tetrachloroethylene, PCE. And they're not very nice substances. You dissolve them in water to some concentration. You introduce them. You do exactly the same experiment. After 16 days, 380 days, and 633 days, you go sticking in a bunch of capillary tubes into the subsurface and sample the fluids to find out exactly what their concentrations are. And you find that they've gone at different velocities downrange. And so if you take for 2 years the chloride plume, the carbon tetrachloride plume, and the PCE plume, these plumes have each gone different lengths. And so the ratios of these lengths that they've traveled should be some magnitude of the retardation. And so it's probably written on the bottom here. It is. So if you take the ratio of 57 meters and divide it by 23.5 meters, that's the retardation coefficient from carbon tetrachloride relative to the conservative tracer. Chloride's conservative. If you take 57 and divide it by 13, that's the retardation factor for the PCE. And so we can define exactly what those are. The ratio of those two are roughly 2 to 1 and 4 to 1. And those define the magnitudes of retardation. And so what we could do from this, if we wanted to, is since we know that retardation is equal to 1 plus the density of the aquifer divided by it's saturated, so it would be porosity, and multiplied by Kd. I suppose if we know this, and we know the density of our aquifer and porosity, or guess it, then we could come up with a value of KD quite readily. And so the next page is just doing that. It's rearranging this term here in terms of KD, calculating from retardation coefficients, which we have here and here. 2.42 minus 1 is 1.42. 4.38 minus 1 is 3.38. Multiplying by some porosity, which I've assumed somewhere. I don't know where. The porosity actually I think is quite low. No, that's not, that's the organic content. Does anyone see porosity on this? Oh yes. 30% porosity, 2 kilograms per liter. So this would be 2,000 kilograms per meter cubed. A liter is a thousandth of a cubic meter. And if you multiply these out, you end up with KD values in terms of 0.213 and 0.507. So somewhat of an academic idea, but a way to be able to get it. And so we don't really need this now because we've got retardation. But if we had alternatively a magnitude of KD, we could calculate exactly what this is and do it in the opposite way. But in this particular case, we've done it in the reverse direction. So that is one way by which we can get an idea of these retardation factors. You can't tell it here because the concentrations aren't marked. But the other thing that you might expect is that, for instance, I guess you could think, oops, I didn't take that. If we looked at the distributions that we had, I don't know where that figure is. Is it here? If you looked at these distributions, I guess you could also think about something else. You might think also that if this was going through here, I suppose you could imagine that instead of going up to this full amount here, it might only come up to here. I guess this would be for the red one, I suppose. So what's the reason for that? Well, if you filled up this portion of the porous medium with this solute, and it removes it and puts it onto the aquifer, I suppose if you took a box and you filled it with grains, and you put in something that was of concentration C1, and you looked at the distribution, it'd be a uniform concentration across the whole thing. So not with time, but with space. I guess this would be C1. And you left it in contact, and you think that over time, a portion of this material would sorb onto the solid, then by definition you lost it to the fluid. So by mass balance, then the concentration has to be reduced. And so in a static system, you'd expect this concentration to be reduced from C1 to something less than C1, and you could calculate it out if you knew what C star was. We won't do it, but you could calculate it. But this has to be lower. And so if that's lower, then you'd expect that this peak here could also be lower as well. And the reason for mentioning that is that we don't know what those concentrations are in this particular top figure because they're not labeled. But you'd expect the peaks of these concentrations to be perhaps higher than the peaks of these, and these to be even less, just from that kind of argument. So we don't know from what's on those figures, but you'd expect that. Yeah.
So is retardation number a property of the aquifer or the fluid?
It's a property of the aquifer and the characteristics of the solute and maybe the solvent as well.
So the density factor in the retardation number equation is the density of the aquifer or the
it's the bulk density of the aquifer. So, but that doesn't, Yeah, so it's the bulk density of the aquifer, but different solutes will have different KDs. So for a given aquifer, this will always be the same, right? It'll always be whatever the density of the aquifer is. The porosity for your aquifer will always be the same. If you have PCE versus carbon tetrachloride, it's changing this value of KD, and therefore through that changing this value of R. If you had something other than water flowing as well, which you won't have, if you had, for instance, pure gasoline flowing, then that would also affect the distribution coefficient between gasoline and the aquifer. So KD would be different. So, in those cases. So the other things there are, so next time, I'm not finished yet, but next time we'll use some standard methods to calculate with only knowing the solutes themselves and water. We'll calculate what the magnitudes of KD are from oxygenol water partition coefficients. So from looking at different solvents, how they partition into organic carbon, we should be able to find out the values of KD from a reference textbook in chemical engineering, from standard tables. So we won't do that today, but this is just to compare those numbers that we get with the values that we got today. So today we got values for KD which are lowest for carbon tet, highest for tetrachloroethylene. As a result, the retardations for these are lowest for carbon tet, highest for perchloroethylene, because they scale directly with this through this equation here. So that's not surprisingly. And we actually have numbers for them, and they're in units of milliliters per gram, I think. Don't quote me on that now, but we'll perhaps go into it in more detail next time. I'm guessing they are in milliliters. Yeah, they may or may not be. We'll see next time. So the other thing is that we've talked about physical sorption by taking it out of the water and attaching it to the solid. So what that looks like is it takes a very sharp front that's traveled a long way downstream and turns it into a less sharp, a canted over front that has traveled less far downstream. And so you can also get that behavior from something that kind of isn't sorption, but ends up looking like sorption. And so the thought exercise is this. If you take a fracture that has an impermeable rock on either side, and you push a solute down it, you get a front which is looking like the ones we've looked at. It will have traveled a length which is equal to, velocity is equal to length over time, so length is equal to velocity times time. Right? And so if now you change the rock on either side and you make it porous, it's got water sitting inside the pores, and therefore now the concentration that comes down here will see the water that's in those pores. It'll see that the concentration is 0 initially, and by Fick's law it will want to diffuse into them. If it diffuses into them, then by definition it's lost to being in the fracture, and therefore the concentration in the fracture should be reduced. So that'll have two effects. It will reduce the concentration in the fracture, and it'll also stop it going downwind or downstream as fast as it would before. So that's even where you don't have any absorption of the solute onto the matrix in the rock fracture around it, you still get something that kind of looked like absorption. And it's merely because it's being taken up and the mass is being lost by being transferred to the water, which is immobile within the pores. If you then make the aquifer reactive, so that in addition to just sitting within the water in the pore space, that concentration can also attach itself to the walls of the grains, then you'd expect to see another effect. And that additive effect would be that first, the concentration that's in the water will attach itself to the pores, and therefore the location of this front will recede as it attaches to the pores here from the porous from the being dissolved in the liquid. And also the concentration that's inside that will be reduced by some amount. And so as a result of being diffusing into the water and being sorbed onto the immobile grains, you get a further reduction in the distance that it's traveled downstream. And so these effects in this would be due to the absorption that occurs, but absorption that was in the rock that's flanking the fracture. And this would be an effect that kind of looks like absorption. The front's not going so far. It's reducing the concentration from a maximum value here, which now is a bit less. And it's not due to any magnitude of absorption at all. It's merely the fact that part of the mass that's involved in the water is present within the water that's immobile within the pore spaces of this rock, and therefore it appears like it's adsorption-like. And so there are effects that we can have that are looking like absorption, but aren't really due to absorption. And we can define what those are, but we won't. So that's it. So we've made the point, if we go back, that non-conservative transport is probably important, because in this case the plume has gone half as far and a quarter as far as the conserved plume, so it's a big effect. We don't know what the concentrations are, but we surmise that these concentrations are higher and therefore more dangerous than these here, for the reasons we've talked about. And so we might also like to find out exactly what these effects would be if we don't have an experiment in situ beforehand to be able to define this, but if we want to define where these locations might be from first principles. So what we'll talk about next time is how to evaluate these magnitudes by evaluating the magnitudes of KD. So we'll attempt to get KD, and we want to get KD because that gives us retardation, which is the same equation. And so if we have a magnitude of this, we can get this, and we can do exactly what we've done today, but not have an experiment to tell us beforehand what our result is, because we'd like to be able to predict it. And it turns out that we can do those things based on the solubility of organics in water, and also another fundamental parameter, which is the octanol water partition coefficient, which is how those coefficients partition between water and organic carbon in the system. So we can define some parameters which we can get out of a book, which will tell us exactly what the KD value should be, and then we can use that to predict what retardation coefficient is, and then we can define the behavior of our system in a forward mode rather than an inverse mode, calculating retardation from an experiment in situ. We want to calculate what the behavior in situ is from our characterization of those media. So that's what we'll do next time. Okay, but that'll be next week, I guess.